Hello and welcome to another calculus video. In this one we're going to be looking at section 6.3. It is another volume method, but this time it's called the shell method. We have 2 bullet points. Find the volume of a solid of revolution using this shell method, and then we can compare the disk and washer with the shell. And here let me just do a graphical idea what's going on. Let's say we have, here's our x-axis, and we are going to find a solid from A to B. If we're doing the disk or washer method, we would start here at the left and we would find a disk and then the next disk. And they might get bigger for a while and then they might shrink for a while. But what we're doing is lining up infinitely many, infinitely thin disks, and we're sort of building this solid from left to right. Or if we were looking straight on the edge, again, like back there, we start with a small disk. Maybe they'll get a little bigger, and then they'll get a little smaller, but these are all disks. So we build our solid from left to right. If we're doing a shell method, we might start way out here with a very infinitely thin. This would be like the outer surface area of our solid, and we would rotate that around our x-axis, so we would have a hollow shell. And then we would come in a little bit closer and do another shell. And then we'd come in closer. So here we're building it sort of from the outside in, as opposed to the disk method where we build it from left to right. Now we're building it from the outside, like its surface area, and then we build our way inside. And what's this? This is going to come up with this stuff here. So in this section, we're going to study an alternative method to find the volume of a solid of revolution. This is called the shell method, but because it uses cylindrical shells. To begin, consider a rectangle as shown in figure 6.2.7. So here's the rectangle, this height. Remember in the last section, we always have this representative rectangle, this representative element. Here it is this rectangle. W is the width of the rectangle. That's this little W here. Height is the height of the rectangle. Here we're laying down, so that's sort of how long it is. P is the distance between the axis of revolution and the center of the rectangle. So here this distance P is from the axis of revolution to the exact center of our representative element. When this rectangle is evolved about its axis of revolution, it forms a cylindrical shell or tube of that same thickness W. To find the volume of the shell, we would need to consider 2 cylinders. The radius of the larger cylinder corresponds with the outer radius of that shell. That would be this here, P plus half W. And the radius of the smaller cylinder corresponds to the inner radius. So that would be P minus half of the width. Because P is the average radius of the shell, here is our outer, P plus half the width. The inner is P minus half that width. So the volume of our shell would be pi times r squared, pi times that P plus half W squared times the height, and then we would subtract the volume of the whole, the inner radius, pi times P minus half of W, that quantity squared times h. If we FOIL out the quantity squared, we will have some things combine and cancel. If you go through all the algebra, you're going to have 2 pi times P times h times W, or 2 pi times the average radius, P, times the height, h, times the thickness, W. We can use this formula to find the volume of a solid of revolution. For instance, the plane region in figure 6.2.8, right here, is revolved about a line to form the indicated solid. Consider a horizontal rectangle of width delta y, that's this yellow rectangle here, as a plane region is revolved about a line parallel to the x-axis. The rectangle generates a representative shell with this volume. Delta volume, the change in the volume, is 2 pi times P of y, that's our distance from our axis of rotation, times h of y, that is the length of our representative element, times dy. We can approximate the volume of a solid by n solid by n such shells of thickness delta y, height h y sub I, and average radius p of y sub I. So the volume of our solid, we would sum up all of those representative elements, those rotations, and then we would get this approximation becomes better and better as our norm approaches 0. Remember, that's when our n goes to infinity. So the volume of our solid is here in our summation notation. And then when we calcify it up, we have this one down below. 2 pi. We will integrate from c to d, some numbers on our x or y axis. In this case, it's our y axis. And then we have p of y, h of y, dy. The p of y is our distance from axis of rotation. Distance from axis of rotation. H of y is the representative element, the height of that rectangle, just like we found back in the last section. And then here, it's good to note, you remember in our last section, every time we did a representative rectangle, it was always perpendicular to the axis of rotation. Here's our axis of rotation. Now our representative rectangle is parallel to the axis of rotation. We are still perpendicular to the axis of integration. So on our integral, we will have c and d numbers from the y-axis, and our function will be in terms of the y variable. But now we are parallel to our axis of rotation. We are always perpendicular to the axis of integration. Oops. Get back there. So here is the shell method to either axis. To find the volume of a solid revolution with the shell method, use one of these formulas. If your axis of revolution is horizontal, here we are rotating around the x-axis. So we will be perpendicular to the y-axis. So our formula is p of y, the distance from the axis of rotation, h of y, the length or height of our representative rectangle, and then dy. If we now go with a vertical axis of revolution, here we are rotating around y. So we are going to be parallel to that axis, meaning we are perpendicular to x. So now our formula is 2 pi. Integrate a to b. Those numbers will come from the x-axis. And we have p of x, our distance from the axis of revolution, h of x, the height of our representative element, and then dx as our variable of integration. And that brings us here to example 1. Find the volume of the solid of revolution formed by revolving the region bounded by the graph of x minus x cubed. That's this sort of parabolic shape here we see in the first quadrant. We want to rotate that, bounded by that and the x-axis from 0 to 1. We are going to rotate around the y-axis. So again, we see this arrow rotating around the y-axis. We are perpendicular to x, so that means everything important here is going to be coming from the x-axis. So I'm going to write out the blank formula for x. We have 2 pi. We will integrate from a to b. And then we have p of x, that is our distance from our axis of revolution. H of x is what determines the height of our rectangle. And then we will have dx for our variable of integration. All right, let's see what we can fill in now. 2 pi is just 2 pi. Our upper and lower bounds, looks like we're going to start accumulating area or volume at 0. And we're going to go out to x is 1. So that'll just be a 0 to 1, lower and upper bounds. Now remember, this p of x is our distance from our axis of rotation. We are rotating around y. So in a lot of these, especially when you are rotating around a coordinate axis, what is our distance away from the y-axis? Well, let's say I'm right here, and that's 1/2. How far away am I from my axis of rotation? 1/2. If I'm right here at 1, 0, how far am I from my axis of rotation? 1. In this case, because our axis of rotation is the y-axis, p of x is just a number on the x-axis. It's some x value. So p of x is just equal to x. H of x, what determines the height of our representative rectangle? Well, here's our rectangle. The top of it is touching the function. The bottom of it is touching 0. So h of x, in this case, is just our function, x minus x cubed, dx. So there's our setup. P of x is our distance from the axis of rotation. When we are rotating around the y, our distance away is just some x number. H of x is the height of our rectangle dictated by the function. And it looks like we are all set up and ready to anti-derive and evaluate. Well, I guess we're not going to anti-derive just yet. We got to do a little algebra first. So let's distribute this x. So now it's going to be x squared minus x to the fourth dx. And now we are ready to anti-derive. So the 2 pi is a constant multiple. That will come along. And then we're going to have x to the third over 3 minus x to the fifth over 5. And we will evaluate that from 0 to 1. All right, upper limit, of course, is going to jump in first. So here's my 2 pi. And now the upper limit 1 jumps in. 1 cubed over 3, that's a 1/3. Minus 1 to the fifth over 5, that is 1/5. So there's our upper limit. And if we plug in our zeros, 0 cubed over 3 is 0. Minus 0 to the fifth over 5 is 0. So those do 0 out nicely. And let's see. What is a third minus a fifth? Well, remember I showed you this in class. If we multiply those denominators, 3 times 5 is 15. And then we subtract right to left. 5 minus 3 is 2. So that becomes 2/15. Don't forget we got to multiply that by this 2 pi out front. So that becomes 2 pi times 2/15, which is 4 pi over 15. Now, they did not give us units for this problem, but remember this is a volume, so keep in the back of your mind this is some unit cubed, because we're talking volume here. All right, what is next? Example 2. Well, that makes sense. Use the shell method to find volume. Find the volume of the solid of revolution formed by revolving the region bounded by the graph of x equals e to the negative y squared. We want to rotate that about, well, it's going to be bounded by that graph and the y-axis 0 to 1. We are going to rotate about the x-axis. So let's analyze our picture. Here's our function, e to the negative y squared. We see our rotational axis is x, and then we see our representative element. So what determines the length of this? Well, the right side of it is touching our function. The left side of it is touching x is 0. So it would be the function minus 0, or just e to the negative y squared. Determines our rectangle. And then here is our distance away from our axis of rotation. Well, if we're rotating around the x, we are looking for our p of y, that is our distance away from the axis of rotation. And just like we saw in the last example, our distance away from the x-axis is just some number on the y-coordinate. If I'm right here, I am 1 unit away from my x-axis, and that also happens to be my distance away from the axis of rotation. It's just a 1. So p of y is just equal to y. So let's write out our blank formula. Volume equals 2 pi. Now, because we're going to the y-axis, the book would use c and d for our lower and upper bounds. And then it's going to be p of y, h of y, dy. And 2 pi is just 2 pi. Remember now, c and d, we are perpendicular to the y-axis, so our upper and lower bounds will be numbers on the y-axis, and we're starting down here at 0, and we're going to 1, so that's going to be 0 to 1. P of y, our distance from axis of rotation, we've already determined is just y. And then we have h of y, that is a height of our rectangle, or just e to the negative y squared, dy. Now I guess I can get the picture out of here. So we've got this to anti-derive. And let's think, what method are we going to use? We've got basically two functions. We've got a y and an e to the negative y squared. So I'm going to assume I have an inner function. I would first assume it's e's exponent. So if I'm going to let u equal negative y squared. Du dy would equal negative 2y, and then we'd put the dy on the other side. So remember in class I call this the rocket fuel. We can't launch our rocket without this rocket fuel. We have the dy, we have the important part, the y, so we do need the negative 2. So I'm going to squeeze a negative 2 in there with red ink, and of course we are going to balance that. We're going to need a negative 1/2 out front with the 2 pi. So let's clean this up a little bit. 2 pi times negative 1/2. So that's going to be a negative pi out there. And then we're going to have our integral from 0 to 1. And I'm going to just reorder this a little bit. We've got e to the negative y squared, and then times negative 2y dy. Okay, so I think we are ready to do a little calculus. We are going to antiderive. So we have our negative pi out front. So when we antiderive this, remember that our inner function's derivative goes away. This is our, quote, rocket fuel. So that's gone. What's the antiderivative of e to the negative y squared? Well, it's just e to the negative y squared. And we will evaluate that from 0 to 1. So, as you well know, our upper limit will jump in first. So we got this negative pi out here, and then 1 is going to jump in. Now be careful, that negative is not, it's not negative y in parenthesis. This is negative y squared. So when the 1 jumps in, we get 1 squared is 1, and it's a negative 1. So that's going to be e to the negative 1. Fundamental theorem says we subtract. Now lower limit 0 jumps in. That's going to be e to the 0. And just to make this look a little prettier, we'll keep our negative pi out there. And then e to the negative 1, well, we could move that downstairs and make it a positive exponent. So that's 1 over e minus e to the 0 power. Anything to the 0 power is 1. On the AP test, I would leave my answer exactly like that. It is very exact. If they ask you to round it to 3 decimal places, we could just punch that in the old calculator, and you'd get about 1.986. And there we go. The volume of that rotational solid via the shell method. Now here's a comparison of these two. Let's see what the book says. The disk washer and shell methods can be distinguished as follows. For the disk and washer, the representative rectangle is always perpendicular to the axis of revolution, whereas in the shell method, the representative rectangle is parallel to the axis of revolution. Remember, you're always perpendicular to the axis of integration, where your upper and lower bounds come from, and the variable that your function will be written in terms of. The washer method and shell method can be compared in the figures. So let's see here. What we got on the left is the disk and washer, and then on the right we have the shell method. Notice on disk and washer it's a pi in front of our integral symbol. For the shell method it's a 2 pi. And then for the disk and washer method, we're dealing with different radii. Here we have outer radius squared minus inner radius squared, outer radius squared minus inner radius squared. But remember, for our new shell method, it's just p of x, h of x dx, or p of y, h of y dy. And again, remember, you are always perpendicular to the axis of integration. Now let's do a little flashback. We did this same one in the last section. Yeah, here it is. When we did the disk method, I can't remember the example number, but here we had to set up 2 integrals. This first one from 0 to 1 was a disk method. And then from 1 to 2 became a washer method, outer radius squared minus inner radius squared. So to pull this one off in the last section, we needed 2 integrals. We are going to revisit that now with our new shell method and see that this is easier to do with our shell method. So first, let's look, I'm going to write out the formula as a blank. Volume equals 2 pi. In the picture, we are perpendicular to x, so we're going to go to the x-axis. I'm going to use a and b. And then we're going to have p of x, h of x, dx. So let's start plugging some stuff in there. We got our 2 pi. We are perpendicular to the x-axis, so that's where the lower and upper bounds will come from, 0 to 1. P of x is our distance from our axis of rotation. We are rotating around the y-axis, so our distance away is just going to be some number on the x-axis. So P of x is just x. H of x, remember, is what is the height of our representative element. Well, here in the picture, the top of that rectangle is touching the equation x squared plus 1. The bottom is touching 0. So that would just be x squared plus 1. And we'll close off those parentheses and give it a dx. So there we go. There's our setup, a single integral setup for this same volume that we needed 2 before in the last section. So first a little algebra to get everything set up. Distribute the x, so that's going to be x cubed plus x dx. And it looks like we're ready to anti-derive and evaluate. So there's our 2 pi. We will raise the power by 1, divide by the new power. Raise the power by 1, divide by the new power, from 0 to 1. So I'm going to keep my 2 pi there. So let's put the upper limit in when the 1's jump in, nice and easy. 1 to the 4th over 4 is a quarter. 1 squared over 2 is a half. There's our upper bound. If we plug in our lowers, we're going to have 0 over 4 plus 0 over 2. Those are just a pair of zeros. So we don't even really need them. So we get a half plus a fourth. That's 3/4. So that'll be 3/4 times the 2 pi over 1. And that would be 6 pi over 4 if we multiply straight across. And if you notice, 6 and 4 are both even, so chop them in half, 3 pi over 2. That is the exact same way, or volume we got when we did that in the last section with the other method. Again, if you want to go back and review that, this is much simpler with the shell method. Okay. Ooh, now here's a good one, a volume of a pontoon. So let's say you're an engineer and somebody's come up with a new seaplane, a floating plane, and they figure out the weight of the plane, and they want a certain volume pontoon that will keep the weight of that plane and any passengers floating on the water instead of sinking to the bottom. So maybe you're an engineer and you're going to be charged with finding a perfect pontoon of some set volume that will keep our float plane afloat. So here, this pontoon is designed by rotating a graph of 1 minus a 16th of x squared between -4 and 4 about the x-axis, where x and y are measured in feet. Find the volume of the pontoon. So I guess our first order of business is to determine, should we use disk or shell? Let's take a look at the picture they provided. Now it looks like the picture they provided is we are perpendicular to our axis of rotation. So yeah, they got this as a disk method. Could we do this with the shell? Imagine I'm trying to lay a red rectangle horizontal, or excuse me, parallel to our axis of rotation. So I got one side of it is touching part of this curve. The other side is touching the other side of it, so it doesn't look like the shell method would even be an option here. So in this case, we are going to do disk. Let me shrink this back down. And I'm going to leave that there so we can see it. So if we think back to the last section, volume is going to be pi. And is this disk or washer? We are touching our axis of rotation all the way across, so this is going to be disk method. We're going to start accumulating at -4. We are going to go up to +4. So we now need here our radius squared. And what is going to determine the height of our representative element here? Well, the top of it is touching our function, 1 minus x squared over 16. So in here, I will put my 1 minus x squared over 16. That's quantity squared, and we'll put a dx out there. All right, it looks like we are set up. We do not have an inner function's derivative, so it looks like we're going to have to FOIL out that binomial before we antiderive. Pi, negative 4 to 4. Let's see if we FOIL that out. First times first is 1. We'll have a minus. If I multiply these together and then times it by 2, that would be 2x squared over 16, or x squared over 8. And then last will be positive. Negative times negative is positive, and we would multiply our numerator by itself, so that would be x to the 4th. And then downstairs, 16 times 16 is 256. And we still got a dx on there. Okay, time to actually antiderive now, and then we will evaluate. Get up there. So we still got our pi here. And now we antiderive with respect to x. 1 will antiderive to a 1x. And then here, we're going to raise our power by 1, so now we're up to x cubed. And we're going to divide by the new power, so there'll be a 3 down there with the 8. If we multiply those, we get a 24. Plus, we're going to raise our x to the 4th up a power to 5. And we'll multiply the denominator already there by another 5, because we're going to divide by that new power. That'll be 1,280. And we will evaluate from negative 4 to positive 4. So this looks like it's going to be fun. So again, pi is out here. And I'll switch to black ink for my upper limit. 4 jumps in. 4 jumps in for x, so that just becomes a 4. Minus 4 cubed is 64, 24ths. Plus 4 to the 5th is 1,024 over 1,280. So there's our upper bound. Minus, I'm going to sort of move down here, put a parenthesis. Now the negative 4 jumps in, so this will be a negative 4. And then when the negative 4 jumps in, since it's odd, the negative will escape and switch that sign. So it's going to be plus 64 24ths. And the same thing here to the 5th. The negative will escape and then hit that plus, change that to a minus now. Minus 1,024 over 1280. And I'll close off that bracket. Okay, now common denominator is going to be nasty. At this point, I would just, if it's on the AP test, I'd hope it's on a calculator part. Remember, I have showed you how to do the fractions on the TI-30s. You could easily do this on a TI-30. It all boils down to 64/15 pi, which is approximately, since we're dealing with an applied problem here, we're talking cubic units, because here we are in feet. 64/15 pi doesn't do much for me, but if we multiply that all out, we get about 13.4 cubic feet cubed. Okay, and there in that one, the disk method is preferable. I don't even know if shell method would be possible. Okay, I think we got one more example in this section. Yes, we do. And this one, oh, what's that? Shell method necessary. In this case, if we wanted to do disk, it'd be impossible. Because here's our function. If we want to solve that and get x by itself, we're not going to be able to do it. So in this case, shell method is absolutely necessary. And last I knew, you will not run into one of these type problems on the AP test. Shell method is not necessary for the advanced placement AB test. It can make a more difficult integral simpler, but you're never going to have one where it's absolutely necessary. Ooh, and notice here too, we are no longer rotating around the x-axis or the y-axis. So here we are rotating around something else, so our p of y or our p of x is not just going to be x or y in this case. So I'm just going to write out the blank formula here. And again, I'm looking back to my picture, and I'm seeing that I'm perpendicular to x, so I know this is everything's going to be in terms of x. We're going to have a 2 pi. We're going to have our lower and upper bounds a and b. And we're going to have a p of x, our distance from axis of rotation, h of x, the height of our representative element, and then a dx. Okay, the easy stuff will be our upper and lower bounds. We're going to the x-axis. Looks like we're going from 0 to 1. Now, p of x. Remember, this is our distance from our axis of rotation. So I think the easiest way to explain that, I'm going to put a set of parentheses here. P of x is our distance from our axis of rotation. If we look at the picture, here is my axis of rotation. What is the farthest away from it I'm ever going to be? Well, that distance is 2 units. So I'm going to put a 2 in there, and then we are going to subtract the x-coordinate, 2 minus x. So let's just do a test run here. Remember, this is our distance from axis of rotation. If I put in the x-coordinate of 0, 2 minus 0 is 2. That is how far away I am from my axis of rotation. Let's see if I put a 1 in there. If I put in x as 1, I would be right here. How far away am I from my axis of rotation? Well, 2 minus 1 is 1. That's my distance away. Now our height of our representative element. So to find that, remember we're going to do top minus bottom. So what is touching the top of my representative rectangle? That is my curve, and that curve is right here, x cubed plus x plus 1. So x cubed plus x plus x plus 1. And now we're going to subtract what's touching the bottom of it. Okay, what's touching the bottom of this is 1 minus 1. So to keep me from rewriting all of this again, I have a plus 1 in blue, a minus 1 in red. Those are going to cancel each other out. So when it's all cleaned up, it's going to look something like that. 2 minus x quantity times x cubed plus x quantity. And I think I can get the picture out of the way now. All right, we are going to have to anti-derive this, and we have a couple of binomials, so it looks like we're going to have to FOIL this out. 2 pi, 0 to 1. Let's see, first times first is a 2x cubed. 2 times x is plus 2x. Negative x times x cubed is minus x to the 4th. And then minus x times plus x is minus x squared. All right, now just because it's the way I roll, I'm going to write that in descending order. So we have a negative x to the 4th plus 2x cubed minus x squared plus 2x dx. All right, that's a big juicy polynomial to anti-derive, but it's just going to be a nice simple power rule. We got a 2 pi, and let's put a bracket there. That's going to be negative x to the 5th over 5, plus that'll be 2x to the 4th over 4, and the 2/4 will reduce down to a half, so that's x to the 4th over 2, minus, raise the power by 1, divide by the new power, x cubed over 3. And then our last 2x to the 1st will become 2x squared over 2, or just x squared. Evaluate from 0 to 1. Ooh, I love 0 to 1. So there's our 2 pi waiting for the end of the problem. And the 1 jumps in, so we're going to have a negative 1/5 plus a half minus a third plus 1. If we plug in minus, then all the 0 will go through and 0 everything out. So it looks like our common denominator, I'm just going to work back up here. Looks like our common denominator is going to be a 30. So we multiply the first one by 6 over 6, negative 6/30. Multiply the 1/2 by 15 over 15, 15/30. 1/3 gets multiplied by 10 over 10, 10/30. Plus 1 would be 30/30. And if we add together all our numerators, again, we still got this 2 pi out here. Everything in the brackets, though, is going to be a 29/30. And then it looks like we can just reduce on the diagonal. Divide by 2, divide this by 2, so that's 15. 29 pi over 15. There were no units on this, so just, cubic units of some sort. All right, I believe that is the end of 6.3, the shell method. Yeah, next time we're in class, we'll do a few odd problems on that. I hope this video was helpful.